In this video, I include some examples of some more advanced functions and their derivatives. The examples were borrowed from a number of reputable fellow educators. I hope you will find the presentation illuminating.
Derivatives of trigonometric functions. To determine the derivative of trigonometric functions, I'm going to start out by graphing one full cycle of the sine curve. You should be familiar with this function from your studies of pre-calculus or math analysis. So from 0 to 2 pi, the graph looks like this. Maximum of 1 and a minimum of -1. So that's how the graph of sine of x looks like. Now, what I'm going to do is I'm going to plot a graph with the inputs corresponding to the radian measure and my output to correspond to the measure of the slope of the tangent line at that given input. Let's start plotting. So as you notice, the tangent line initially is positive. Specifically, it has a value of 1. So my first point is 0, 1. So now let's see what happens when you graph more points. So initially, the tangent line is still positive, so my output should still be giving me positive values. But then slowly, the slope of the tangent line attains a value of 0. Attains a value of 0 at pi over 2. At this point, the slope of the tangent line becomes negative. So I start getting negative values for the output. And then as I head towards pi and head towards 3 pi over 2, the slope of the tangent line is once again slowly achieving a value of 0 until it achieves it at 3 pi over 2. And then at this point, the slope of the tangent line becomes positive once more, so the values of the output are positive. So there we go. There's one full cycle. So now looking at the blue graph, it looks awfully familiar. And indeed, this is the cosine function. So it turns out that the derivative of sine of x is actually cosine of x. Pretty neat, huh? Okay, so now that we know how to find the derivative of sine of x, let's try to figure out what the derivative of cosine of x is equal to. So just like the previous example, I'm going to graph one full cycle of the cosine curve. A maximum of 1 and a minimum of -1. So this is one full cycle of cosine of x. And again, just like the previous example, I'm going to graph the value of the tangent line at every single x value. Okay, so let's do just that. You notice our first point here, the value of the slope of the tangent line is equal to 0. So our first point is actually 0, 0. So as we generate points, the slope initially is negative. So we should expect to get a negative output for our graph. And then as it transitions to pi over 2, it begins to slowly attain a value of 0. Until the value of the tangent line is actually 0 at pi. So here, the tangent line is 0. And then from here, the tangent line becomes positive, so the values become positive. And as it approaches 3 pi over 2, the slope of the tangent line slowly attains a value of 0, and finally achieves a value of 0 at 2 pi. Hard to see at first, but the red graph is actually an inverted sine curve. So it turns out that the derivative of cosine is actually the negative of sine. Pretty cool. Okay, so now that we know what the derivative of sine and cosine is, we can find the derivative of other trigonometric functions. Let's find the derivative of tangents. Find the derivative of f of x equals tangent of x. First, we need to rewrite this function in terms of sine and cosine. Remember, tangent of x can be rewritten as sine over cosine. In other words, a quotient. we can use the quotient rule to find a derivative. So rewriting the expression as sine over cosine and letting f of x to be equal to sine of x and g of x to be equal to cosine of x, we can use the quotient rule as follows. The derivative of r of x is going to be equal to cosine of x times the derivative of sine of x minus sine of x times the derivative of cosine of x, all over cosine of x squared. So applying appropriate differentiation rules, we get that the derivative of sine is cosine, and the derivative of cosine is negative sine. Simplifying expression gives us the following. Now here, we could rewrite the expression cosine squared plus sine squared of x using one of the trigonometric identities back from pre-calculus class. Remembering that the identity cosine squared of x plus sine squared of x equals 1, we can substitute the numerator with just 1. So the derivative of r of x is going to be equal to 1 over cosine squared of x. And remembering that the reciprocal of cosine is secant, and the reciprocal of secant is 1 over cosine, we can rewrite the expression as secant squared of x. So in the end, the derivative of tangent is equal to secant squared of x. So with this, we add another trigonometric derivative to our list. Let's find some more. Find a derivative of cosecant of x. Okay, so remembering that the reciprocal of sine is cosecant, and the reciprocal of cosecant is 1 over sine, we can rewrite this expression as r of x equals 1 over sine of x. Here we let f of x to be equal to 1 and g of x to be equal to sine of x. Using the quotient rule, we have that the derivative of r of x is going to be equal to sine of x times the derivative of 1 minus 1 times the derivative of sine of x, all over sine of x squared. Applying appropriate derivatives and simplifying the expression gives us the following. Now here, what we want to do is we want to rewrite this expression. So we could break up the denominator as follows to give us the expression negative times 1 over sine of x times cosine of x over sine of x. Now 1 over sine of x is the same thing as cosecant of x. So we rewrite that. And cosine over sine is just another way of writing cotangent of x. So the final derivative of r of x is equal to negative cosecant times cotangent of x. By using the quotient rule, you can find the derivative of the reciprocal trigonometric functions. And I encourage you to derive the derivative for secant and cotangent in the same manner. Check your answer with the following table. Here we have the derivative of all 6 trigonometric functions. You really don't need to memorize all the derivatives, only that of sine and cosine. As we just saw in the previous problems, we can derive all the other derivatives by applying the quotient rule. But if you really want to memorize the table, here's a tip. Notice that the minus signs go with the derivatives of the co-functions, specifically cosine, cosecant, and cotangent. Okay, let's finish off this video with a final example. Find a derivative of r of theta equals cosecant of theta times the quantity of theta plus cotangent of theta. We have a product of functions, so this is a perfect candidate for the product rule. I'm going to let f of theta to be equal to cosecant of theta and g of theta to be equal to theta plus cotangent of theta. Applying the product rule, we have that the derivative of r of theta is going to be equal to cosecant of theta times the derivative of theta plus cotangent of theta plus the quantity of theta plus cotangent of theta times the derivative of cosecant of theta. Okay, so simplifying the expression and distributing gives us the following, and further distributing gives us the following expression for the final derivative of the function. Alternatively, we could rewrite this expression as follows. We could factor out a cosecant of theta, and using one of the other trigonometric identities, okay, again, you should have learned this from pre-calculus class, 1 plus cotangent square of theta equals cosecant square of theta. So we could substitute this expression for cosecant square of theta, which gives us the following. Simplifying it further, the ones cancel out, and we distribute the negative sign. And then here we collect like terms And then here, we factor out a negative and a cotangent of theta. So an alternative form for the answer for the derivative of r of theta is equal to negative cosecant of theta times cotangent of theta times the quantity of 2 times cotangent of theta plus theta. So in our next video, we're going to learn the chain rule. And with this final derivative rule, we could essentially find any derivative in calculus. Implicit differentiation, level 1. Recall that when we express functions using equations, we typically write them with the independent variable, usually x, and the dependent variable, usually y, separated by an equal sign, so that the dependent variable is explicitly expressed in terms of the independent variable. For example, the equation of a line in slope-intercept form expresses the variable y explicitly as a function of x. Here, the dependent variable y is written explicitly in terms of the independent variable x. In other words, y is a function of x. Now let's compare the same equation of a line defined implicitly by relation between x and y, the dependent and independent variable respectively. The equation of a line is expressed using the standard form of the line, as opposed to the slope-intercept form of the line. Notice that one variable is not explicitly defined as a function of the other variable. Nevertheless, f is still a function of x, and this is very important to remember. I repeat, y is still a function of x. If you remember from your studies of Algebra 2 and pre-calculus, you actually dealt with implicit functions when you learn about conic sections, specifically circles, ellipses, parabolas, and hyperbolas. If you recall, the equation of a circle with radius 5 and centered at the origin is given by the implicit equation x squared plus y squared equals 25. We need to find the derivative of this function. What do? We are fairly good in finding derivatives of functions whose independent variable is explicitly expressed in terms of the other variable. So one course of action is to solve for y. Let's do just that. So we have the implicit equation x squared plus y squared equals 25. We solve for y by subtracting x squared from both sides. And we have y squared equals 25 minus x squared. So now we take the square root of both sides. And now remember, when you take a square root, you usually get two answers, a positive and a negative answer. So we actually have positive, negative, the square root of 25 minus x squared. Notice that we need to take a derivative of two functions, the positive and the negative function. In order to take a derivative of the positive function, we rewrite the expression into a derivative-friendly form. So the derivative of this function is going to be equal to 1/2 times the quantity 25 minus x squared raised to the power of negative 1/2 times negative 2x. And that of the negative expression is the same thing, but we just add the negative sign. Notice that we end up with two functions, the positive function, which represents the upper half of the circle, and the negative function, which represents the lower half of the circle. This means that we need to find the derivative of two distinct functions. Finding the derivative of these functions yields the following. Okay, well, this function was relatively easy because we were able to express y explicitly in terms of x, but you ended up taking the derivative of two functions. In general, if you use this approach, you will waste precious time. Not only do you have to algebraically manipulate the function to solve for y, but you might end up with two or more separate functions, which then you have to individually find the derivatives of each one. That sounds like a hassle. Fortunately, we can use the method of implicit differentiation. This consists of differentiating both sides of the equation with respect to x, and then solving the resulting equation for the derivative. Let's see this technique in action. Find a derivative of x squared plus y squared equals 25. We are going to use a combination of Leibniz notation and prime notation to find a derivative. Remember, whatever you do to one side, you have to do to the other side of the equal sign to maintain equality. You should have learned this concept back when you were in Algebra 1. All these concepts build one over another. So the first step is to take a derivative of both sides. So taking a derivative of both sides, we have the following. When using Leibniz notation, the expression d over dx can be treated as a variable. Here we actually have to distribute the dy over dx over x squared and y squared. So now, the derivative of x squared is just 2x. The derivative of y squared is a different story. Remember I told you to remember that y is a function of x. So here we actually have to use a chain rule. So the way you want to think about this is remembering that y is a function of x. We could rewrite the derivative of y squared as the derivative of f of x raised to the power of 2. And now here, the outer function is x squared and the inner function is f of x. So applying the chain rule, we have that the derivative of y squared is going to be equal to 2 times f of x times the derivative of f of x. Or in different notation, you can rewrite this as 2 times y prime. Or in a different expression, we could rewrite this as 2 times y times dy over dx. So here, dy over dx is the same thing as y prime, which is the same thing as f prime of x. They're all just different ways of expressing the same idea. And here, the derivative of a constant is just 0. So we end up with the expression 2 times x plus 2 times y prime equals 0. Now, the whole point is to find the derivative of y with respect to x, or to find y prime. So now the next step is to solve for y prime. So up to this point, it just becomes a typical algebra 1 problem, where you just solve for a variable, in this case, y prime. So adding negative 2x to both sides, we have the following. And dividing by 2y to isolate the y prime, we have the following. The 2's cancel out, so now we have that the derivative is equal to negative x over y. Notice that the final expression contains the independent variable and the dependent variable. This is typical when you find derivatives of implicit functions. If you really want it in terms of x, then substitute y with the explicit form of the equation, as follows. So we see that we get the same answer as we did when we found the derivative the long way. And again, I emphasize that you remember that y is a function of x. In order to find a derivative, we need to apply the chain rule at all times. You could think of this idea using Leibniz notation as follows. The derivative with respect to x is going to be equal to the derivative of y times the derivative of y with respect to x. And remember, this is just an application of the chain rule. All right, in our next video, we are going to work on some examples. Implicit differentiation, level 2. All right, let's jump straight into some examples. Find the derivative of the expression 2x plus 3x squared plus x times y equals 4. So we have an implicit function. So the first step is to take a derivative of both sides. Distributing the derivative sign, we have the following. And so we have that the derivative of 2x is just equal to 2. The derivative of 3x squared is just equal to 6x. And now here, we need to notice that we actually have two functions. So we need to apply the product rule. So applying the product rule, with f of x being x and g of x being y, we have that the derivative expression is going to be equal to x times the derivative of y plus y times the derivative of x. And remember, in order to take the derivative of y, we need to apply the chain rule. So we have that the derivative of y is going to be equal to the derivative of y times dy over dx. The derivative of y is just 1. So we just end up with dy over dx, which is the same thing as y prime. And continuing on with the product rule, we have y times the derivative of x, and the derivative of x is just 1. And finally, the derivative of a constant is just 0. So we have the following expression. And then now the next step, after we take derivatives, is to solve for y prime. So again, up to this point, it becomes a standard algebra 1 problem, where we have to solve for y prime. Subtracting 2, 6x, and y to the other side, we have the following. And dividing by x, we have that the final derivative, dy over dx, is going to be equal to the negative of 2 plus 6x plus y over x. And once again, the derivative is expressed in terms of y and x. Let's try the next one. Find the derivative of 1 over x plus 1 over y equals 2. First step is to take derivative of both sides. Derivative of 1 over x is the same thing as the derivative of x raised to the power negative 1. And the derivative of 1 over y is the same thing as the derivative of y raised to the power of -1. And the derivative of a constant is just 0. So now, the derivative of x raised to the power of -1 is just an application of the power rule. Negative x raised to the power of -2. Now here, the derivative of y raised to the power of -1 requires the application of the chain rule. Remember, y is a function of x, so we need to apply the chain rule. So applying the chain rule, we have the derivative of y raised to the power of -1 times dy over dx. And this is equal to negative y raised to the power of -2 times y prime. So substituting all those values into the expression, we have the following. And once again, we solve for y prime. So we have the following expression. And the final derivative is going to be equal to negative x raised to the power of -2 over y raised to the power of -2. And remembering that negative exponents can be rewritten by taking its reciprocal, we have that the final derivative is equal to y squared over x squared. All right, let's try the next one. Final derivative of x squared times y plus x times y squared equals 3x. All right, like always, we take a derivative of both sides, distribute the negative signs to each term. We are going to have to end up taking a derivative of x squared times y. So here, notice that we have a product of two different functions. So we need to apply the product rule. In addition, in the next term, we also have a product of two functions. So we also need to take the product rule. And the derivative of 3x is just equal to 3. So let's take care of the product rule here. I'm going to let f of x be equal to x squared and g of x to be equal to y. Applying the product rule, we have x squared times the derivative of y plus y times the derivative of x squared. So once again, the derivative of y is just y prime, and the derivative of x squared is just 2x. So we have the following expression. Now let's take care of the next product. So the derivative of x times y squared is going to be equal to x times the derivative of y squared plus y squared times the derivative of x. The derivative of y squared is going to be equal to the derivative of y times dy over dx. So that gives us that the derivative of y squared is going to be equal to 2y times y prime plus y squared, because the derivative of x is just 1. So now we need to solve for y prime. So it's not going to be that easy. The first thing we need to do is we need to get all the y primes on one side of the equation sign and get everything else on the other side of the equation sign. So doing that, we have the following. And the reason why we want to do this, get all the y primes on one side, is that the end goal is to factor out the y prime out of the expressions, like so. We solve for y prime by dividing by the expression x squared plus 2xy. So that gives us that the final derivative is equal to 3 times negative 2xy minus y squared over x squared plus 2xy. So more complicated derivative requires you to actually factor out the y prime term from the expression in order to ultimately solve for it. Let's try the next one. Find the derivative of y times sine of x squared equals x times sine of y squared. First step, take a derivative of both sides. And notice here that we need to apply the product rule. So the product rule is going to give us y times the derivative of sine of x squared plus sine of x squared times the derivative of y. In addition, the other side also requires the product rule. So that's going to give us x times the derivative of a sine of y squared plus sine of y squared times the derivative of x. So carrying out the product rule, we have that the derivative of sine of x squared is going to be equal to cosine of x squared times 2x after applying the chain rule, and the derivative of y is just y prime after applying the chain rule. Now going to the other side of the equal sign, we have that the derivative of sine of y squared is going to be equal to cosine of y squared times 2y times y prime. So notice that we actually applied the chain rule twice. And the derivative of x is just 1. This expression signifies to the following. The next step is to solve for y prime. The way you want to do this is get all the terms that have the y prime term into one side and everything else to the other side of the equation side. So doing that, we have the following. And factoring out the y prime, the expression signifies to the following. And solving for y prime, by dividing by this entire expression, we have that the final derivative is going to be equal to 2xy times cosine of x squared minus sine of y squared over 2xy times cosine of y squared minus sine of x squared. Let's try the next one. Find the derivative of e raised to the power of x squared times y equals x plus y. We take derivatives of both sides, and here we are going to have to use a combination of the chain rule and the product rule. So the derivative of e raised to the power of x squared times y is going to be equal to e raised to the power of x squared times y times the derivative of x squared times y, which in itself requires the application of the product rule. So applying the product rule, we have x squared times y prime plus y times 2x. Going to the other side of the equal sign, we have that the derivative of x is just 1, and the derivative of y is going to be equal to y prime. So we have the following expression, and once again, we want to get all the terms that have the y prime into one side and everything else to the other side. Doing that, we have the following. Factoring out the y prime, we have the following expression, and finally, the final derivative after solving for y prime is going to be equal to 1 minus 2 times xy e raised to the power of x squared times y over x squared times e raised to the power of x squared times y minus 1. All right, let's try the final example. Find the derivative of tangent of x minus y equals y over 1 plus x squared. Applying derivatives to both sides, we have the following. And so the derivative of tangent of x minus y is going to be equal to secant squared of x minus y times 1 minus y prime. And the derivative of the other side, okay, notice that we have a quotient. So we need to apply the quotient rule. Our f of x is going to be equal to y, and our g of x is going to be equal to 1 plus x squared. So applying the quotient rule, we have the following. Now that we've taken derivatives, we need to get all the terms with the y prime to one side and everything else to the other side. In order to do this, we distribute the secant squared of x minus y to the quantity 1 minus y prime. So we have the following. And then what we do is we add secant squared of x minus y times y prime to both sides. So we have the following expression. And here what we want to do is we want to add these values by finding a common denominator. Doing so, we have the following expression. So now that we have a common denominator, we can add the expressions. So that reduces to the following. We multiply by the denominator both sides. We have the following expression. And here, finally, are able to factor out the y prime. And solving for y prime, we have that the final derivative is equal to the quantity 1 plus x squared raised to the power of 2 times secant squared of x minus y plus 2xy over the quantity 1 plus x squared plus secant squared of x minus y times the quantity of 1 plus x squared raised to the power of 2. So for the most part, you will probably find the derivative of easier functions. These examples show just how complicated these derivatives can be. All right, so armed with the technique of implicit differentiation, we will learn how to find the derivative of inverse trigonometric functions in our next video. Of inverse trigonometric functions, level 1. In the previous video, we learned how to find derivatives of functions where the dependent and the independent variables were related implicitly. Now we use this new technique to find the derivative of inverse trigonometric functions. If you're rusty on this concept, I advise you to check the video on inverse trigonometric functions in the pre-calculus section. Assuming that inverse trigonometric functions are differentiable, and in fact, if f is any one-to-one differentiable function, such as f of x equals sine of x, it can be proved that its inverse, arch sine of x, is also differentiable, except where its tangents are vertical. This is possible because the graph of a differentiable function has no corner or kink. So if we reflected about the line y equals x, the graph of its inverse function also has no corner or kinks. Recall the definition of arc sine. This function accepts values of x, and its corresponding output represents the angle, typically in radians. Remember during your pre-calculus class that you actually used this function to find angles when you had knowledge of the measure of the opposite side and the hypotenuse of a right triangle. In contrast to the sine function, where its inputs are angles and its outputs are ratios between 1 and -1 inclusive. So taking the graph of sine of x and reflecting it about the line y equals x, we have the following graph. Notice that we restricted the domain in order to make this relation a function. In other words, it passes the vertical line test. In addition, notice that the domain and range are switched. That is to say that the value of x, the domain, on sine of x becomes the value of y, the range, for arc sine. And the values of y, the range, for sine of x becomes the values of x, the domain, for arc sine. Now looking at the graph of arc sine, we further define it to be restricted to quadrants 1 and 4 in the unit circle. In other words, the corresponding range of arc sine is between -pi/2 and pi/2. Okay, now let's use y to represent the dependent variable and x to represent the independent variable. If this is the case, we can write the arc sine function as follows. Taking the sine of both sides, we can rewrite the expression by remembering that the composition of a function and its inverse undo each other, leaving you with the independent variable. So you end up with the following expression. Sine of y equals x, where the values of y is restricted to the interval -pi/2 and pi/2, quadrants 1 and 4 on the unit circle. So the purpose of that manipulation was to rewrite the function into a relation defined implicitly. So now we can use the techniques from the previous video to find a derivative. The first step to take a derivative of the implicit functions is to take a derivative of both sides. So the derivative of sine of y is going to be equal to cosine of y times y prime. The derivative of x is just equal to 1. Second step is to solve for y prime. So solving for y prime, we have that the derivative is going to be equal to 1 over cosine of y. Now, in order to rewrite cosine of y in terms of x, we need to substitute cosine of y with an expression in terms of x. The way we do this is by using a familiar identity. Specifically, cosine squared of y plus sine squared of y equals 1. One of the Pythagorean identities, back from pre-calculus class. So here, what we want to do is solve for cosine of y. So doing that, we have cosine squared of y equals 1 minus sine of y squared. And taking the square root of both sides, we have that cosine of y is equal to positive negative 1 minus sine of y raised to the power 2. Now here, we have two answers, a positive and negative square roots. Now, which one should we use? Well, if we revert back to the definition of sine inverse is defined in quadrants 1 and 4, specifically between -pi/2 to pi/2. In those quadrants, cosine of y attains positive values, so it makes sense to use the positive square roots. So doing so and substituting values for y, the value for y from our original expression was actually y equals sine inverse of x. Carrying out the substitution, we have the expression 1 over the square root of 1 minus sine of sine inverse of x raised to the power 2. So the composition of a function and its inverse undo each other, leaving you with the independent variable x. So it turns out that the final derivative of arc sine or sine inverse is equal to 1 over the square root of 1 minus x squared. The derivative of inverse cosine can be found in a similar fashion. The derivative of arc cosine, also known as inverse cosine, can be found as follows. We take the cosine of both sides, so we have the following expression. And now that we have an implicit function, we take a derivative of both sides. So the derivative of cosine of y is going to be equal to negative sine of y times y prime, and the derivative of x is just 1. Solving for y prime, we have the derivative is going to be equal to negative 1 over sine of y. Once again, we need to substitute sine of y with an expression in terms of x. Just like the previous problem, what we're going to do is use one of the Pythagorean identities to substitute sine of y with an appropriate equivalent expression. So sine of y is going to be equal to the square root of 1 minus cosine squared of y. Once again, we have two answers, positive and negative. And in order to choose which one to use, we need to go revert back to the definition of cosine inverse. Cosine inverse is defined in quadrants 1 and 2 in the unit circle. In other words, between 0 and pi. In this interval and in these quadrants, sine of y attains a positive value, it makes sense to use the positive expression. So doing that, we have the negative of 1 over the square root of 1 minus cosine of cosine inverse of x raised to the power of 2. So once again, a function and its inverse undo each other, leaving you with an independent variable. So we have that the final derivative is equal to negative of 1 over the square root of 1 minus x squared. The derivative of tangent inverse and cotangent inverse can be found using the same procedure and reasoning. The derivative of cosecant and secant inverse depend on the definitions that are used for these functions. Let's find the derivative of inverse secant. We define secant inverse, or arcsecant, as the number between 0 and pi, whose secant is x. We could differentiate secant inverse of x by using the same techniques that we use in finding arcsine and arccosine. But there's a much easier way. Notice the following. If an angle has secant equal to x, then it has cosine equal to 1 over x. This means that arcsecant of x is the same thing as arccosine of 1 over x. So now we differentiate both sides with respect to x using the chain rule and the derivative of inverse cosine. The derivative of arcsecant is what we're trying to find. In order to take a derivative of arccosine, we apply the chain rule along with the power rule. We have the following expression. And instead of the expression, we have that the derivative of arcsecant is equal to 1 over x squared times square root of 1 minus 1 over x squared. We can simplify the equation, but it has to be done carefully, since the square root of x squared is not equal to x when x is negative. So doing some algebraic manipulation, we could rewrite the denominator as follows. We add the fractions underneath the square root sign. So doing so, we have the following. We take the square root of the numerator and that of the denominator. We have the following. The expression in the denominator, the square root of x squared, you should remember this is the definition of the absolute value. So substituting the square root of x squared with the absolute value, we have the following expression. And here, notice that x squared over the absolute value of x is the same thing as just the absolute value of x. If you don't believe me, go ahead and try it out. Plug in some numbers, and you'll find out that the expression x squared over the absolute value of x is the same thing as the absolute value of x. So substituting x squared over the absolute value of x with that of the absolute value of x, we have the final derivative of arcsecant is equal to 1 over the absolute value of x times the square root of x squared minus 1. The derivative of inverse cosecant can be found in the same manner. I advise you to try it out as an exercise and compare it with the following table. Here we have the derivative of all the inverse trigonometric functions. Notice that the negative sign goes with the co-functions, specifically inverse cosine, cosecant, and cotangent. The inverse trigonometric functions that occur most frequently are inverse sine, cosine, and tangent. Derivatives of inverse trigonometric functions, level 2. All right, let's jump straight to some examples. Differentiate the expression y equals 1 over inverse sine of x. One of the common errors in dealing with inverse trigonometric functions is the notation itself. Many students believe that the expression for sine inverse represents the reciprocal of that function. This is a common mistake, and make sure you don't fall for it. This is why we have a second way of expressing inverse trigonometric functions, by calling it arcsine as opposed to sine inverse or inverse sine. The proper way to mathematically represent the reciprocal of a function is as follows. So in this side example, sine of x is raised to the power of -1, which is the same thing as 1 over sine of x, which is equal to cosecant of x. Just keep a side note that the -1 on the inverse trigonometric functions does not represent an exponent, unless the entire expression is raised to the power of -1. So knowing that, we could rewrite the expression as follows. Sine inverse of x raised to the power of -1. So now that we have it in a differentiable friendly form, we take a derivative. We need to use a combination of the power rule and the chain rule. The outer function is x raised to the power of -1, and the inner function is inverse sine. So the derivative of y with respect to x, or y prime, is going to be equal to -1 times sine inverse raised to the power of -2 times 1 over the square root of 1 minus x squared. Simplifying the expression, we have that the final derivative is equal to the negative of 1 over sine inverse raised to the power of 2 times the square root of 1 minus x squared. You can rewrite sine inverse as arc sine. Other answers are acceptable. Let's try the next one. Differentiate the expression y equals sine inverse of 2x plus 1. So here we need to apply the chain rule with the outer function equal to sine inverse of x and the inner function equal to 2x plus 1. Applying the chain rule, we have the following. 1 over the square root of 1 minus 2x plus 1 raised to the power of 2 times 2. Simplifying the expression algebraically and expanding the binomial on the bottom, we have the following. Now here we factor out a 4, and by factoring out a 4, we could take a square root of 4, which ends up being 2, and that cancels out with a 2 in the numerator, giving us the final expression to be equal to 1 over the square root of negative x squared minus x. All right, let's try the next one. Differentiate the expression cosine inverse of e raised to the power of 2x. Once again, this is a perfect candidate for the application of a chain rule. The outer function is cosine inverse, and the inner function is e raised to the power of 2x. Find the chain rule, we have that the derivative is going to be equal to negative of 1 over the square root of 1 minus e to the power of 2x raised to the power of 2 times e to the 2x times 2. Simplify the expression, we have that the final derivative is equal to negative of 2 times e raised to the power of 2x over the square root of 1 minus e raised to the power of 4x. All right, let's try the next one. Differentiate expression arctangent of arcsine of the square root of x. Here we have nested functions, so we have to use the chain rule twice. For the first chain rule, we have that the outer function is arctangent and the inner function is arcsine of the square root of x. So applying the chain rule twice, we have that the derivative is going to be equal to 1 over 1 plus the arcsine of the square root of x raised to the power of 2 times 1 over the square root of 1 minus the square root of x raised to the power of 2 times 1/2 x raised to the power of negative 1/2. We have the final derivative is equal to the following. The next one, differentiate the expression x times the arctangent of the square root of x. So here we have a product of two different functions. One function is x, and the second function is arctangent of the square root of x. So we need to apply the product rule. I want to let my f of x equal x and my g of x equal arctangent of the square root of x. So applying the product rule, we have that the derivative is going to be equal to x times the derivative of tangent inverse of the square root of x plus tangent inverse of the square root of x times the derivative of x. Derivative of tangent inverse of the square root of x requires the use of the chain rule, along with the power rule. So taking the derivative of tangent inverse of the square root of x, we have the following. And that simplifies to 1 over 2 times the quantity 1 plus x times the square root of x. And the derivative of x is just 1. So substituting the values for the derivatives, we have the following expression. Now here, x and the square root of x simplify to the square root of x. So we have that the final derivative is going to be equal to the square root of x over 2 times the quantity 1 plus x plus tangent inverse of the square root of x. Alternatively, we can rewrite tangent inverse as arctangent. Let's try the next example. Differentiate the expression arctangent of the quantity x minus the square root of 1 plus x squared. So here we're going to use the chain rule. So applying the chain rule, we have the following expression. And to simplify this expression, we have the following. Expanding the binomial yields the following. Here we add expressions to have a common fraction. And over here, we simplify the expression in add-like terms. And now here we factor out a 2 from the expression, and we multiply numerator and denominator. We group the term 1 plus x squared so that we could factor it out. So factoring out a 1 plus x squared from the denominator, we have the following expression. And here, the square root of 1 plus x squared minus x cancels out with the expression in the denominator, giving us a final answer to be equal to 1 over 2 times the quantity 1 plus x raised to the power of 2. All right, let's try the final example. Differentiate the expression r of x equals e raised to the secant inverse of 1 over x. we could rewrite the expression 1 over x as x raised to the power of negative 1. So here we have nested functions. So we are going to apply the chain rule twice. So applying the chain rule twice, we have the following expression. Simplifying the expression directly, we have the following. Now here, what we want to do is add the terms by getting a common denominator, taking the square root of both the numerator and the denominator. Square root of x squared is the same thing as the absolute value of x. This combines with the other absolute value term. And then here, what happens is that x squared over the absolute value of x squared cancel each other out. So we have that the final derivative is equal to the negative of e raised to the power of secant inverse of 1 over x over the square root of 1 minus x squared. In our next video, we're going to learn how to take a derivative of logarithmic functions. Derivatives of logarithmic functions. To find a derivative of logarithmic functions, we use implicit differentiation. And like always, we are assuming that logarithmic functions are differentiable. And this is possible because logarithmic functions are the inverse functions of exponential functions, which are differentiable themselves. So letting x represent the independent variable and y represent the dependent variable, and a representing the base of the logarithm, we can write the general form of a logarithmic function as follows. F of x equals log base a of x. We can rewrite the expression as y equals log base a of x. Now here, what we want to do is we want to exponentiate both sides of the equation. The right side of the equation simplifies to x because the composition of a function and its inverse undo each other, leaving you with the independent variable. Now that we have an equation written implicitly, we use implicit differentiation to find the derivative. We first take the derivative of both sides. The derivative of the left side of the equation requires the use of the derivative rule we derived in our previous video, specifically the derivative of an exponential function. So applying the derivative of an exponential function along with the chain rule, the expression on the left-hand side of the equation reduces to a raised to the power of y times the natural log of a times y prime. And the derivative of a power function of degree 1 is equal to 1. Now we solve for y prime. Doing so gives us the following expression. We want an expression in terms of x only. We need to substitute the dependent variable y with an expression in terms of x. So we use the original explicit function we started with. Substituting this expression and simplifying, we have that the final derivative is equal to 1 over x times the natural log of a. So we have that the derivative of a logarithmic function is equal to 1 over x times the natural log of a. So now check this out. If the base of the logarithm is equal to e, we would be dealing with the natural logarithm. So if we substitute the base with e, the derivative of a natural logarithm will be equal to 1 over x. As you can see, the derivative of a natural logarithm is relatively simple. And this is why you will encounter natural logarithms frequently in your study of calculus. Another variation of the natural logarithm that appears frequently in calculus is the natural logarithm of the absolute value of x. In order to find the derivative of this function, we need to remember the definition of the absolute value. Recall that the absolute value function is defined as follows. The function will be equal to x when the values of x are positive, and it will be equal to negative x when the values of x are negative. In essence, we need to analyze the function by breaking it into two regions. Applying the definition of the absolute value to the natural logarithm, we have the following. So to find the derivative of the function, we need to take the derivative of the first region, which is equal to 1 over x, and then we take the derivative of the second region, which requires the application of the chain rule. So it turns out that the derivative of the natural logarithm of negative x is equal to 1 over x. So regardless of what region we decide to focus, the derivative of the natural logarithm of the absolute value of x is just equal to 1 over x. So next time you see this function, don't panic. It's just equal to 1 over x. All right, let's go over some examples. Find a derivative of f of x equals the natural log of x cubed plus 7. Checking out the function, we see that it is formed by a composition of functions, where the outer function is the natural logarithm and the inner function is x cubed plus 7. This requires application of the chain rule. So we find the derivative of the outer function and evaluate it at the inner function, and then multiply it by the derivative of the inner function. Simplify the expression, we have that the derivative of f of x is equal to 3x squared over x cubed plus 7. Let's try the next one. Find the derivative of g of theta equals the natural log of sine of theta. So here we also have a composition of functions where the outer function is equal to the natural log and the inner function is equal to sine of theta. So taking the derivative of the natural logarithm and evaluating it at sine of theta, we have the following, and multiplying that by the derivative of sine of theta. So simplifying the expression, we have that the derivative is equal to cosine of theta over sine of theta, which can be rewritten as cotangent of theta. All right, for the next one, let's switch the inner and outer functions and find its derivative. Find the derivative of h of x equals sine of the natural log of x. So once again, we have a composition of functions, but here the outer function is sine of x, and the inner function is the natural log of x. Once again, we take the derivative of the outer function, which ends up being cosine of x, and we evaluate it at the natural log of x. And then we multiply that by the derivative of the natural log of x, which is equal to 1 over x. Simplifying the expression, we have that the derivative is equal to cosine of the natural log of x over x. Let's try a function of a logarithm with a base other than e. Find the derivative of h of x equals log base 3 of 5 minus 2x. So once again, we have a composition of functions. The outer function is log base of 3, and the inner function is 5 minus 2x. Taking the derivative of log base of 3, we have that it's equal to 1 over 5 minus 2x times the natural log of 3. And when we multiply the expression by the derivative of the inner function, we have that the final derivative is equal to negative 2 over the quantity 5 minus 2x times the natural log of 3. You will rarely be taking the derivatives of logarithms of a base other than e. But if you don't panic. Make sure you include the natural logarithmic term into the derivative. Let's try the next example. Find the derivative of h of x equals the natural log of x squared plus 1 over x minus 1. So here, once again, we have a composition of functions. The outer function is the natural log, and the inner function is the quantity x squared plus 1 over x minus 1. So applying the chain rule, we take the derivative of the outer function and evaluate it at the inner function. We have the following expression, and multiply that by the derivative of the inner function. The derivative of the inner function requires application of the quotient rule. So applying the quotient rule, we have the following expression. Simplifying the expression, we have the following. We collect like terms in the numerator, which simplifies to the following. And right here, we cancel out an x minus 1 term, which reduces to the following. And simplifying the expression, we have that the final derivative is equal to the quantity x squared minus 2x minus 1 over the quantity x squared plus 1 times the quantity x minus 1. Okay, now let's solve the same problem a different way. We are actually going to use the algebraic properties of logarithms to rewrite the function. Recall from your studies of Algebra 2 that if we have a logarithm of a quotient, you can break it into a difference of logarithms. In other words, the natural log of x over y is equal to the natural log of x minus the natural log of y. So before we take a derivative, let's rewrite the expression as follows. You can rewrite the expression as the natural log of x squared plus 1 minus the natural log of x minus 1. So now that we have a difference of logarithms, we apply the difference rule and we take a derivative of each term. So taking a derivative of the first term, we have that's going to be equal to 1 over x squared plus 1 times 2x minus the derivative of the natural log of x minus 1, which is equal to 1 over x minus 1 times 1. Simplifying the expression, we have that the final derivative is equal to the quantity 2x over x squared plus 1 minus the quantity 1 over x minus 1. The expression can be left as it is. But if you are not convinced that this is the same answer we got using a different method, I recommend that you algebraically manipulate the expression by using a common denominator. You will discover that you end up with the same answer. So it looks like you learned those algebraic properties of logarithms back in Algebra 2 for a reason. We could use them to rewrite the logarithm into a sum and difference of logarithms. or into a product of two terms whenever possible to make the function easier to differentiate. All right, let's try the next one. Find the derivative of g of x equals the natural log of the expression 2x plus 1 raised to the power of 2 times the expression 5x minus 3 raised to the power of 3. Once again, rewrite the logarithm using the algebraic properties of logarithms. So here we have a product of two terms, so we can rewrite the logarithm as a sum of logarithms. Doing so, we have the following. And so here we can use the property of logarithms to bring down the exponents, which gives us the following expression. And then now we can take a derivative of each term using the sum rule. Taking the derivative of the first term we have, that's going to be equal to 2 times the quantity 2 over 2x plus 1 plus 3 times the quantity 5 over 5x minus 3. To define expression, we have that the final derivative is equal to the quantity 4 over 2x plus 1 plus the quantity 15 over 5x minus 3. Finding the common denominator and adding like terms, we write the expression as 50x plus 3 over 10x squared minus x minus 3. Either answer is acceptable. Okay, let's try the final example. Find the derivative of r of x equals the natural log of the absolute value of 3 minus 2x minus 5x to the power of 3. The derivative of a natural logarithm of the absolute value of x is just equal to 1 over x. So here we apply the chain rule, where the outer function is the natural logarithm, and the inner function is 3 minus 2x minus 5x cubed. So taking the derivative of the natural logarithm, evaluating it at the inner function, we have the expression 1 over 3 minus 2x minus 5x cubed times the derivative of the inner function. So taking the derivative of the inner function, we have the following expression. And simplifying the expression, we have that the final answer is equal to the quantity negative 2 minus 15x squared over 3 minus 2x minus 5x cubed. We could factor out a negative on the numerator and the denominator, and we could rewrite the final answer as 15x squared plus 2 over 5x cubed plus 2x minus 3. In our next video, we are going to exploit the algebraic properties of logarithms to rewrite complicated functions into a more manageable form to save precious time and effort. Logarithmic differentiation, level 1. The calculation of derivatives of complicated functions involving products, quotients, or powers can often be simplified by taking logarithms and exploiting the algebraic properties to simplify the function into a derivative-friendly form. The steps required for logarithmic differentiation is as follows. First, take the natural logarithm of both sides of the equation y equals f of x and use the laws of logarithms, specifically the product to sum law, the quotient to difference law, and the exponent to multiplier law to rewrite the function. Second, differentiate implicitly with respect to x. And lastly, solve the resulting equation for y prime, or dy over dx. Be on the lookout for functions where the range of the function is less than 0 for some values of x. Recall that the natural logarithm function is not defined for values of x that is less than 0. We can fix this small glitch by taking the absolute value of both sides and using the derivative of a natural logarithm of the absolute value of x to compute the derivative. All right, let's see this technique in action. Find a derivative of g of x equals the quantity 3x plus 2 raised to the power of 4 times the quantity x raised to the power of 3 minus 2 raised to the power of 5. First step, rewrite g of x as a dependent variable y, and then we take the natural logarithm of both sides. The whole point of taking natural logarithms is to simplify the expression into a derivative-friendly form by using the laws of logarithms to rewrite the function. So here we have a product of two different functions. So we go apply the product to sum rule to rewrite the expression as follows. In addition, we could bring down the exponents in each term. And now here, the function 3x plus 2 attains negative values at given x values. In order to take the natural logarithm, we need to actually take the absolute value of this function. Likewise, the function x cubed minus 2 also attains negative values. So we also need to take the natural logarithm of the absolute value of this function. So now that we rewrote the function into a derivative-friendly form, we take derivatives of both sides. The derivative of the left-hand side is going to be equal to 1 over y times y prime after applying the chain rule. The derivative of the natural logarithm of the absolute value of 3x plus 2 is going to be equal to 1 over 3x plus 2 times 3, where we apply the chain rule to find the derivative of the inner function, plus 5 times the derivative of the natural log of the absolute value of x cubed minus 2. Here, we apply the chain rule with the outer function equal to the natural log and the inner function equal to x cubed minus 2. Taking a derivative, we have that's going to be equal to 1 over x cubed minus 2 times 3x squared. Simplifying the expression, we have the following. And now, the third and final step is to solve for y prime. So here we multiply both sides by y, and we have the following expression. And lastly, we want the derivative in terms of x only. So here what we want to do is substitute y with the original function we started with. Doing that, we have that the final derivative is going to be equal to the quantity 3x plus 2 raised to the power of 4 times the quantity x cubed minus 2 raised to the power of 5 times the quantity 12 over 3x plus 2 plus 15x squared over x cubed minus 2. You can also simplify the last quantity by finding a common denominator and simplifying. And if you do, you end up with the following expression. For the most part, don't bother rewriting the expression into a different form. The first form is sufficient. Let's try the next one. Find the derivative of r of x equals the square root of x times e raised to the power of x cubed times the quantity x squared minus 1 raised to the power of 5. All right, first step, let's replace r of x with y. And then we take the natural logarithm of both sides. And then we use the properties of logarithms to rewrite the expression into a derivative-friendly form. And here, since we have a product of 3 functions, we rewrite them as a sum of logarithms as follows. And then for the first term, we rewrite the square root of x as x raised to the power of 1/2. We bring down the 1/2, and we take the absolute value of x, since the function x attains negative values as specific domain values. And for the second term, we bring down x cubed, and for the third term, we also bring down the exponent 5, and we have the following expression. Now here, the natural logarithm of e is just equal to 1. So the second expression simplifies to x cubed. And now we take the derivative of both sides. The derivative of the left-hand side is going to be equal to y prime over y. And for the right side, the first term is going to be equal to 1 over x plus 3x squared. And the third term requires the use of the chain rule. The outer function here is the natural logarithm, and the inner function is x squared minus 1. Notice that we take the absolute value because the function x squared minus 1 attains negative values at given domain values. So taking the derivative, we have that's going to be equal to 1 over x squared minus 1 times 2x. Simplifying the expression, we have the following. And then lastly, we need to solve for y prime. So we multiply both sides by y. And here we substitute y with the original function we started with. So in the end, the final derivative is going to be equal to the square root of x times e raised to the power of x cubed times the quantity x squared minus 1 raised to the power of 5 times the quantity 1 over 2x plus 3x squared plus 10x over x squared minus 1. So for the final example, let's try one which requires all 3 laws of logarithms. Find the derivative of h of x equals the cube root of the quantity sine of x squared times tangent of x raised to the power of 4 over the quantity x squared plus 1 raised to the power of 2. All right, so first step, we need to substitute h of x with y. And then we take the natural logarithm of both sides. We rewrite the cube root as a fraction of power, and then we use the property of logarithms to bring down the 1/3. And then here, what we do is we use the property of logarithms to rewrite the product into a sum and the quotient into a difference. Doing so gives us the following expression. Then here we distribute the 1/3 to all 3 terms. So we have the following. And now we bring down the corresponding exponents on each term. We use the property of logarithms to bring down the 2. And since sine of x attains negative values at corresponding x values, we need to apply the absolute value. In the second term, we also bring down the exponent, and we apply the absolute value since tangent of x also attains negative values at corresponding x values. And in the last term, we bring down the 2. Notice that x squared plus 1 is always positive. It does not require the application of the absolute value symbol. So now we take the derivatives of both sides. The derivative of the left-hand side is again equal to y prime over y. And here, the derivative of the natural log of the absolute value of sine of x is going to be equal to 1 over sine of x times cosine of x. The derivative of the natural log of the absolute value of tangent of x is going to be equal to 1 over tangent of x times secant squared of x. And lastly, the derivative of the natural log of x squared plus 1 is going to be equal to 1 over x squared plus 1 times 2x. So in the final expression, we have the following. And the final step is to solve for y prime. We multiply both sides by y. We have the following. And here, we substitute y with the original function we started with. The final derivative is going to be equal to the cube root of sine of x squared times tangent of x raised to the power of 4 over the quantity x squared plus 1 raised to the power of 2 times the quantity 2/3 cotangent of x plus 4 times secant squared of x over 3 times tangent of x minus 4x over 3 times the quantity x squared plus 1. Okay, and there you have it. That's how you use logarithmic differentiation to find the derivative of complicated functions involving products, quotients, and powers. In our next video, we will use logarithmic differentiation to find the derivative of functions of the form f of x raised to the power of g of x. Logarithmic differentiation, level 2. Before we continue using logarithmic differentiation, you absolutely need to be able to distinguish the various cases in which exponents and bases can be used to form a function. In general, there are 4 different cases. In the first case, both the base and the exponent are constants. As a result, the function simplifies into a constant. An example of this function is the expression y equals 5 raised to the power of 3, which simplifies to 125. As a consequence, the derivatives of these functions are equal to 0. In the second case, the base is formed by a function, and the exponent is a constant. In other words, these expressions are power functions. For example, the expression y equals x to the power of 4. As a result, the derivatives of these functions require the use of the power rule, and at times the chain rule. The third case is formed when the base is a constant and the exponent is a function. An example of these expressions are the exponential functions like y equals 3 to the power of x. The derivative of these functions is equal to itself times the natural log of the base times the derivative of the exponent after applying the chain rule. The last case is when the base is formed by a function and the exponent is also formed by a function. For example, the expression y equals x raised to the power of x. To find the derivative of these functions requires the use of logarithmic differentiation to bring down the exponent by using the laws of logarithms, and then solving for the derivative dy over dx or y prime. Okay, let's give it a shot and find the derivative of this particular function. Find the derivative of y equals x raised to the power of x. Alright, the first step in logarithmic differentiation is to take the natural logarithm of both sides. Then we apply the laws of logarithms to rewrite the function. The main reason why we need to use logarithms is to bring down the exponents as follows. Now that we've brought down the exponent, we take the derivative of both sides. The left-hand side of the equation is equal to 1 over y times y prime. The right-hand side of the equation requires the application of the product rule. So it's going to be equal to x times the derivative of the natural log of x, which is equal to 1 over x, plus the natural log of x times the derivative of x, which is equal to 1. The left-hand side simplifies as follows. And the right-hand side simplifies to 1 plus the natural log of x. After we have taken the derivative of both sides, we solve for dy over dx or y prime. So here we multiply both sides of the equation by y. And we have the following expression. Lastly, we need to substitute y with the initial expression we started with. So substituting the expression, we have that the final derivative is equal to x raised to the power of x times the quantity 1 plus the natural log of x. So the only complicated part of this problem is the fact that you need to be able to identify the type of functions that require logarithmic differentiation to find its derivative. Let's try the next example. Find the derivative of y equals x raised to the power of sine of x. Once again, the first step in logarithmic differentiation is to take the natural logarithm of both sides. Then we apply the laws of logarithms to rewrite the function. We bring down the exponent and we take the derivative of both sides. The left-hand side of the equation is once again equal to 1 over y times y prime. The right-hand side of the equation requires the application of the product rule. So it's going to be equal to sine of x times the derivative of the natural log of x, which is equal to 1 over x, plus the natural log of x times the derivative of sine of x, which is equal to cosine of x. The left-hand side simplifies as follows, and the right-hand side simplifies to sine of x over x plus the natural log of x times cosine of x. After we have taken the derivative of both sides, we solve for dy over dx, or y prime. So here we multiply both sides of the equation by y, and we have the following expression. Lastly, we need to substitute y with the initial expression we started with. Substituting the expression, we have that the final derivative is equal to x raised to the power of sine of x times the quantity sine of x over x plus the natural log of x times cosine of x. Alternatively, we can find a common denominator on this expression, and here we use the rules of the exponents to simplify the left-hand expression as x raised to the power of sine of x minus 1. Either expression is acceptable. So now let's take the same problem but switch the base and the exponent. Find the derivative of y equals sine of x raised to the power of x. Okay, so we take the natural logarithm of both sides, then we apply the laws of logarithms to rewrite the function as follows. We bring down the exponents and we take the derivative of both sides. The left-hand side of the equation is once again equal to 1 over y times y prime. The right-hand side of the equation requires the application of the product rule. So it's going to be equal to x times the derivative of the natural log of sine of x, which is equal to 1 over sine of x times cosine of x after applying the chain rule, plus the natural log of sine of x times the derivative of x, which is equal to 1. The left-hand side simplifies as follows, and the right-hand side simplifies to x times cotangent of x plus the natural log of sine of x. After we have taken the derivative of both sides, we solve for dy dx, or y prime. So here we multiply both sides of the equation by y, and we have the following expression. Lastly, we need to substitute y with the initial expression we started with. Substituting the expression, we have that the final derivative is equal to sine of x raised to the power of x times the quantity x times cotangent of x plus the natural log of sine of x. Let's try the next one. Find a derivative of y equals the natural log raised to the power of cosine of x. Okay, so we take the natural logarithm of both sides, then we apply the laws of logarithms to rewrite the function as follows. We bring down the exponent and we take the derivative of both sides. The left-hand side of the equation is once again equal to 1 over y times y prime. No surprise there. The right-hand side of the equation requires the application of the product rules. So it's going to be equal to cosine of x times the derivative of the natural log of the natural log of x, which is equal to 1 over the natural log of x times 1 over x after applying the chain rule, plus the natural log of the natural log of x times the derivative of cosine of x, which is equal to negative sine of x. The left-hand side simplifies as follows, and the right-hand side simplifies to cosine of x over x times the natural log of x minus sine of x times the natural log of the natural log of x. After we have taken the derivative of both sides, we solve for y prime. So here we multiply both sides of the equation by y, and we have the following expression. Lastly, we substitute y with the initial expression we started with. Substituting the expression, we have that the final derivative is equal to the natural log of x raised to the power of cosine of x times the quantity cosine of x over x times the natural log of x minus sine of x times the natural log of the natural log of x. We could rewrite the right side of the expression by finding a common denominator and simplifying, but it's not really needed. All right, let's try the final example. Find a derivative of x raised to the power of y equals y raised to the power of x. Okay, so here notice that we have an expression written implicitly. So we have to use implicit differentiation. But before we do that, notice that we have exponents that are functions themselves. So we need to take the natural logarithm of both sides. Then we can apply the laws of logarithms to bring down the exponents and rewrite the function as follows. Now we take the derivative of both sides. The derivative in the left-hand side requires the application of the product rule. The derivative is going to be equal to y times the derivative of the natural log of x, which is equal to 1 over x, plus the natural log of x times the derivative of y, which is equal to y prime. And the right-hand side also requires the application of the product rule. So taking the derivative we have, that's going to be equal to x times the derivative of the natural log of y, which is equal to 1 over y times y prime after applying the chain rule, plus the natural log of y times the derivative of x, which is equal to 1. Simplifying the expression, we have the following. Now we need to solve for y prime. The only way we can do this is to bring all the terms that contain the y prime expression and bring them to one side, and all the other terms to the other side. Doing that, we have the following. Now that we have all the terms with y prime in one side, we can factor out the y prime. Once we do that, we can solve for y prime, so we divide both sides by the quantity natural log of x minus x over y. We simplify the expression as follows, and it turns out that the final derivative is equal to x times y times the natural log of y minus y squared over x times the natural log of x minus x squared. Remember, when you are finding the derivative of an implicit function, your final answer will be written in terms of the independent variable x and the dependent variable y.
Hi. Now in this tutorial, what I want to show you is that if we're given a parametric equation, something like above here, how do we find dy dx? How do we find the gradient at any point on the curve? Well, you can do it quite easily without having to find the Cartesian equation, without having to express y in terms of x. And the way we do it is through the chain rule. The chain rule, remember, is dy by dx always equals dy over some d something, as long as you times it by the same d something over dx. So what is that d something? Well, in the case when you've got your parameter as t, then we would use dt. I'll show you another example later on where we do a trigonometric parametric equation. So in order to find dy dx, then we use the chain rule. So what is dy by dt? Well, we can take this and we can see that dy by dt, if we differentiate it in the usual way, the first term is going to be 6t, second term will be plus 2, and the differential of the constant here is 0. So we've got dy by dt. Now when it comes to dt dx, well, the way around that is that we find dx by dt rather than dt by dx. dx by dt would be just simply 5. So it follows from this that dt by dx is 1 over dx by dt. In other words, 1/5. So we can put these two ideas together and find dy by dx. So therefore we have that dy by dx equals dy by dt, which is simply 6t plus 2, and we multiply that by dt by dx, the 1/5. And what you end up with is 6t plus 2 all over 5. Now some people quite often don't write this particular result. Knowing that you're going to have to find dx by dt, you can often see this quoted as dy by dt but instead of this result they just simply divide by dx by dt, which is essentially another way of looking at this then. We could have said dy by dt, 6t plus 2, divided by dx by dt, the 5, 6t plus 2 all over 5. Well, you don't have to have just equations in this particular format. You can have trigonometric types, and here's an example. You could have, say, x equals 3 sine t and y equals 4t plus cos t. So if we had to find dy by dx, we'd do much the same kind of thing as we did here. You might even like to pause the video if you're happy with differentiating trigonometric functions and have a go. Okay, well, let's just see how you got on if you did have a go. Well, we find dy by dt first. So we've got dy by dt equals differential of 4t with respect to t is just 4. Differential of cos t is going to be minus sine t. And for dx by dt, differential of 3 sine t is going to be 3 cos t. So therefore, when it comes to dy by dx, we've got dy by dt divided by dx by dt. So dy dt is 4 minus sine t, and we can think of it as divided by dx by dt, which will be 3 cos t. And you can't really do that much with that. Okay, well, I've got another one for you to try. Okay, here it is. X equals 1 over t squared plus t, and y equals t squared minus 1 over 2t cubed. So just try and find dy dx and simplify your answer as much as possible. Right, well, let's see how you got on. Well, we're going to need to find dx by dt, so I would want to simplify this term. Think of it as t to the minus 2, and then we've got plus t. So when it comes to differentiating this with respect to t, dx dt equals minus 2t to the minus 3, and then if we differentiate that plus t, we end up with plus 1. And I'd prefer to simplify this, rewrite this plus term first, so we have 1 minus, and then for this term 2 over t cubed. Okay, so that's dx by dt. When it comes to differentiating y with respect to t, we've got dy by dt equals, well, we're going to first of all need to tidy this up actually, so I'm going to change this term to minus t to the minus 3 over 2. So when it does come to differentiating this, we get for the first term 2t, and differentiating this term we have plus 3t to the minus 4 all over 2. And tidy this up, we get 2t plus 3 over 2t to the 4. So therefore for dy by dx we have dy by dt, so that's going to be 2t plus 3 over 2t to the 4, and that is all divided by dx by dt, 1 minus 2 over t cubed. So you can see we need to simplify this now, and the way I would do this is to times top and bottom by 2t to the 4, because I can see that t cubed goes into 2t to the 4. I'll just write it in red here, times top and bottom by 2t to the 4 over 2t to the 4, as if we're multiplying by 1. It doesn't alter the value of this, just the appearance. So when we multiply 2t with 2t to the 4, we get 4t to the 5. And for this second term, this 2t to the 4 would cancel out with this, just leaving me with the plus 3. And then, when it comes to the bottom, it'll be 1 times 2t to the 4, which will be 2t to the 4. And then for this term, the t cubed will cancel into the 2t to the 4, just leaving me with 2t. So it'll be 2 times 2t, which will be the minus 4t. Okay? Now you could even leave it like that, but do you notice that the denominator factorizes? So I think I'll take that opportunity to factorize it. And if we do that, we can pull out 2t as a common factor, and then we have got t cubed minus 2. Alright? So that's how you do parametric differentiation. Later tutorials I'll show you how we can apply this to finding the gradient at any point on a curve, at particular points, the equations of tangents, normals, and locating stationary points. So I hope you'll have a look at those. And Hi there. Now in this video what I want to do is show you how we find the second derivative for a parametric equation in terms of the parameter. And to illustrate this, I've got this example here where we've got this parametric equation x equals t squared and y equals t to the power 5 minus 2t cubed plus 1. Now the first thing we need to do is find the first differential dy by dx. And I'm assuming that you're already familiar with this, that you've watched the tutorials on how to do this. If not, do go back and check them out. But briefly, we need to find dx by dt and dy by dt first of all. And if you do that, you should find dx by dt is 2t and dy by dt is 5t to the power 4 minus 6t squared. And then we pick up on the chain rule, that is dy by dx is equal to dy by dt times dt by dx. It's as if those dt's cancel out and leaves you with dy by dx. But most people prefer to look at it like this, where we have dy by dt divided by dx by dt. Remember, dt by dx is the same as 1 over dx by dt. So we can have this rule here. And so if we use this rule, then dy by dx will be dy by dt divided by dx by dt. And that gives us 5t to the power 4 minus 6t squared all over 2t. And then if I pull out, say, t squared as a common factor, then I get this result. And the t will then cancel into the t squared. So we end up with t times all of 5t squared minus 6 divided by 2. And if I expand that, because it will be easier in the next stage, we end up with 5t cubed over 2, and then we have minus 6t over 2, which is the same as minus 3t. Okay, so now we've got this far, we now go on to the stage that I really want to show you, which is how we go about finding d2y by dx squared, the second differential then. Okay, now to do this, remember this means to differentiate with respect to x dy by dx. So that means that we need to differentiate with respect to x what dy by dx is. And in this example you can see it's 5t to the power 3, 5t cubed all over 2 minus 3t. Now, because this is a function of t, we can't differentiate it at the moment with respect to x. What we do though is we have a workaround, and we basically apply the chain rule again. I'll put this in square brackets. What we do for this part then is differentiate with respect to t the function that we've got here, dy by dx expressed as a function of t. In other words, 5t cubed over 2 minus 3t. And then, let's just finish this square bracket off. Because we introduce this dt, we multiply it by dt by dx. Again, it's as if these dt's cancel, just leaving me with d by dx as we had here. So I can go ahead now and differentiate what was dy by dx, a function of t, with respect to t. And I end up with 15t squared over 2. And then for the minus 3t, that's just going to be minus 3. I'll put that all in brackets. And then we multiply it with dt by dx. Well, we know that dx by dt is 2t, so dt by dx is 1 over 2t. So if I put 1 over 2t there, and then just expanding this, we end up with 15t over 4. Remember, the t here will cancel into the t squared. And then we've got minus 3 over 2t. And that is essentially the method that we use. So if I just show you that method basically up here, when you're asked to find d2y by dx squared and give it as a function of the parameter, in this case t, then we have that d2y by dx squared is to differentiate dy by dx with respect to x. That's that step here. But then I take dy by dx, which is a function of t, and differentiate it with respect to t. Here we are here. And multiply it by dt by dx. And that takes you then through to your answer. Okay, well, I hope that's been of some use to you. And that is the method then that we apply for any parametric equation. Hi. Now, what I've got here is a typical example of what you could be asked about equations of tangents and normals to parametric curves. And this is an interesting question. I've picked this purely because it develops quite a lot of essential features. So we'll work through this, or you might like to pause the video if you feel that you would like to have a go. But what we've got here is find the equation of the tangent and normal to the curve, the parametric curve, x equals t squared and y equals t cubed minus t. And we've got to find that equation of tangent at the point 4, minus 6. Now to do this, what I would normally encourage you to do is to sketch the curve. Now, you don't have to necessarily sketch the exact curve to do this. I just don't want you to be afraid of not having a go. Now, I know that this is not the curve, okay, but it's just to give you an idea of how you can make headway regardless, get to appreciate the problem. What we've got here is a point 4 minus 6. So if we go 4 minus 6, let's just suppose that point's there. 4 minus 6. And we've got some curve, some parametric curve going through this point. Okay, I'm going to pretend I don't know what it looks like. Let's just draw some kind of curve coming through here. Let's say it's that. And I want to find the equation of the tangent to the curve at this point. Well, in this sketch it looks as if it's going to be something like that. And to find the equation of a tangent, being a straight line, I'm going to use the form y minus y1 equals m bracket x minus x1, a form that hopefully you're familiar with. x1, y1 is a point on the line. That's okay, we've got it here. It's 4 minus 6, the x-coordinate is the 4, and the y-coordinate is the minus 6. M, though, is the gradient, and we've got to get the gradient at this point. How do we do that? Well, differentiation. we need to find dy by dx. So in order to find dy by dx, we need to find dx by dt and dy by dt and use the chain rule. So let's start off then with finding dx by dt. Dx by dt, if we differentiate this with respect to t, we're going to get 2t. And also we have dy by dt is going to equal, well, differential of t cubed is going to be 3t squared, and the differential of minus t is going to be minus 1. So we know that to find dy by dx equals, by the chain rule, dy by dt times dt by dx. Or you might like to think of this as dy by dt divided by dx by dt. That's another version saying exactly the same thing. Either way, what you come up with for dy by dx is, let's just use this version. It's going to be dy dt 3t squared minus 1 divided by dx dt, the 2t. If you use this version, you've got to say that dt dx is 1 over 2t and multiply it with the 3t squared minus 1. You'll come out with the same result. So we've got dy dx, we've got m, the gradient at any point on the curve. The question is, since this depends on t, then we need to find out what the t value is at the point 4, minus 6. And this is a point that's quite interesting here, that you've got to be very careful with. To do this, to find the t value, turn to the easier of these two equations, which I think has to be x equals t squared. We know that x is 4 at this point, so we can say that when x is 4, we know that 4 will equal the t squared. And what does that imply? Well, to get t will be the square root of 4. And the square root of 4 is not just 2, remember it is plus or minus 2. So we've got, for this particular example, two values of t. Question is, which one of those two values is the true one? 2 or minus 2? How do we check? Well, what we've got to do is turn to the corresponding y value. We want a t value that is consistent with not only the x but also the y value. So if we took when t was 2, what does y come out to be? Well, y is equal to t cubed minus t. So if we were to do t is 2, 2 cubed minus 2 turns out to be 8 minus 2, which is 6. That's no good, because we wanted minus 6. Don't necessarily assume that it must be minus 2. You might have made a mistake earlier on in your calculations. I would check it out. So let's just try out when t equals minus 2. What do we have? For y, we've got minus 2 all cubed minus the t value, minus minus 2. So here we get minus 8 plus 2, which is minus 6. Great. Okay, that's what we wanted. So clearly we can see that the t value at this particular point is when t equals minus 2. So we can make progress now. We can get the value of m, the gradient at this point. So we can say that when t equals 2, what is dy dx going to be? Well, dy by dx is going to equal 3 times minus 2 squared. Let's just write it in, show a bit of working, okay? Then minus 1, and that's all divided by 2 times minus 2. So work it out, and what you should find you get is 11 on the top over minus 4, which is minus 11 over 4. So that's the gradient of our tangent here. So when it comes to finding the equation of the tangent, we're in a good position. So just write an intro here now. We can say equation of tangent at the point here, 4 minus 6, is, so what's it going to be? Well, it's going to be y minus y1 there, which is the minus 6, equals m, the gradient, which is minus 11 over 4, times x minus x1. x1 is the 4. So all we need to do is just tidy this up. And if you say multiply by 4 and rearrange it into the format, say ax plus by plus c equals 0, I'll leave you to do that. What you should find you get is 11x plus 4y minus 20 equals 0. Now when it comes to finding the equation of the normal, the line perpendicular to our tangent here, then the gradient is going to change. How does that gradient change? Well, we should know it is the negative reciprocal of the gradient of the tangent. So we know that the gradient of the normal will be plus 4/11. So when it comes to the equation of the normal, let's just write that in, equation of the normal at 4 minus 6, what's that going to be? Well, it's going to be y minus y1, so that's minus 6 equals m, the gradient, which we've seen now is going to be 4/11, so that'll be 4/11, the negative reciprocal then of this. Bracket x minus x1, x minus 4. And again, if we wanted to write this in the form ax plus by plus c equals 0, just times through by 11, rearrange, and what you should find that you get is 4x minus 11y minus 82 equals 0. Okay? Just leave it up to you to check that out. Well, I hope that's given you some idea then how we can find equations of tangents, normals to a curve. And you don't really need to have the exact curve drawn in. But just for the record, if you did want to know what that curve looked like, well, I will draw it in for you. So I'll show you what it looks like. Well, if we draw our axes, we can say that when t is 0, can you see that x will be 0 and y will be 0? So it will go through the origin. And also, when t is 1, x is 1, but y is 0. So we have a point here at 1, 0. And that occurs when t is 1. Now if you put values of t greater than 1 into this equation, you'll see that y grows at a faster rate than x. And x stays positive and y stays positive. So the curve is going to look something like this, going to rise very rapidly like that. When we go between 0 and 1, x remains positive going between 0 and 1, and y though is negative. So the curve comes round here like this. Now for negative values of t, we end up with a reflection of this part of the curve in the x-axis. So the curve goes round and then back down like this. Now the point that we were doing, the point 4 minus 6, was down here. So that was our point 4 minus 6. And when we had our equation of a tangent, then we had a line something like this. And the normal, well, that would have been a line at right angles. Okay, so I hope that's given you some idea then of how we can do this even though we didn't have a sketch of the curve.
We've learned enough math up to this point that many of the mysterious buttons on a sophisticated calculator have been elucidated. There are trig functions, inverse trig functions, logarithms, exponential functions, and lots of other things that are now well understood. But on certain calculators, you may also see these symbols, which look like sine, cosine, and tangent, but with the letter H tacked on at the end. What are these things? These are called hyperbolic functions. They are kind of like the trigonometric functions, except whereas the trig functions are related to the unit circle, hyperbolic functions are related to the hyperbola. Hopefully we remember what a hyperbola is. The hyperbola is one of the conic sections we learned about, the tricky looking one where the cross section goes from the base of one cone through to the base of the other, making a shape kind of like a double parabola. So how do hyperbolic functions relate to the hyperbola? Well, let's look at hyperbolic sine x. This is equal to e to the x minus e to the negative x over 2. Now, what does this mean graphically? Well, let's take this expression and break it up into two terms. 1/2 e to the x minus 1/2 e to the negative x. If we sketch these two curves, we get a hyperbola. And the sum of these two curves at every point will give us hyperbolic sine, which we can see crossing the origin and then getting closer and closer to either section as we go to positive and negative infinity. The domain and range are both all real numbers. So from this, we can see how hyperbolic sine, which can be expressed with these exponential terms, is intimately linked with this hyperbola. What about hyperbolic cosine? That will be the same as hyperbolic sine, we just switch this minus to a plus. That means that the part of the hyperbola that was below the x-axis is now above it, and if we add up these curves, we get hyperbolic cosine, which will look a bit different. This one has a domain of all real numbers, but the range will be from 1 to positive infinity. Hyperbolic tangent will just be hyperbolic sine over hyperbolic cosine, and that will look like this, with horizontal asymptotes at -1 and 1. And then we can have hyperbolic versions of cosecant, secant, and cotangent, which are just the reciprocals of these first three, as we might expect from our knowledge of trigonometric functions. What can we do with these hyperbolic functions? Well, there are a number of identities to be aware of, and they will actually look quite familiar if we remember our trigonometric identities, from expressions with squared functions to these two sum formulas. Amazingly, even the derivatives of hyperbolic functions will be very predictable if we remember the derivatives of trigonometric functions. Here they are, with very few discrepancies from their trigonometric counterparts, just a negative sign here or there. This isn't too surprising if we look at hyperbolic sine and differentiate. We recall that the derivative of e to the x is e to the x, and so the only thing that will change is that for the second term we use the chain rule and bring the negative sign from the exponent down here to cancel out the other one to give us a plus sign. That makes this expression equal to hyperbolic cosine, and all the other derivatives can be found this way as well. Now, just as there are inverse trigonometric functions, there are inverse hyperbolic functions as well. These are denoted this way, and we can get their graphs by reflecting the regular hyperbolic functions across the line y equals x. Hyperbolic sine and tangent pass the horizontal line test, meaning that their inverses pass the vertical line test and qualify as functions. For hyperbolic cosine, the horizontal line test will fail, so we have to restrict the domain to greater than or equal to 0, and from that we can get the inverse function. If we want to express the inverse hyperbolic functions in terms of x, we can swap x and y and then solve for y, as we are used to. See how we bring the 2 up here, then multiply through by e to the y to get rid of that negative exponent, since e to the y times e to the negative y is 1. Then we notice that this is actually in the form of a quadratic equation, since e to the 2y is just e to the y quantity squared. If we use the quadratic formula, we end up with this expression for e to the y, and then to solve for y, we just take the natural log of both sides. So here are the expressions for the 3 inverse hyperbolic functions. These inverse hyperbolic functions are also differentiable, so let's take the derivative of inverse hyperbolic sine. Given the composite function, we need the chain rule. The derivative of natural log requires getting the reciprocal of what the log is operating on, and then multiplying by the derivative of what was inside. And for that, this x becomes 1, and then the radical term requires another chain rule. 1/2 this term to the negative 1/2 times the derivative of what's inside, which is 2x, and we get this. Now we just change the number 1 to get a common denominator, so that we can combine the 2 terms in the parenthetical. And then we can combine these 2 larger terms. We find that this more complicated term will simply cancel out, and this is what we are left with. Doing similar work will get us the rest of these derivatives for the other inverse hyperbolic functions, which are shown here. So that covers the basics regarding hyperbolic functions. We now understand the relationship these have with the hyperbola and how to express them using these exponential terms. We can also take their derivatives, their inverses, and the derivatives of their inverses.